What is reinforcement learning?
It's when an agent learns by doing stuff in an environment and getting rewarded or punished based on what it does. Basically, trial and error with a side of math.
How's it different from supervised learning?
No labeled data. You get feedback only after doing stuff, not beforehand, like life.
Who's the agent?
The decision maker. Like me trying to pick lunch based on past satisfaction and minimal regret.
And what's the environment?
Everything outside the agent's playground or war zone.
Define reward signal?
That's sweet you did good pat on the back from the environment. Or a nope if I mess up.
What's a policy?
The agent's strategy. Like, if I see state X, I do action Y. Unless I'm angry, then all bets are off.
What about the value function?
Tells you how good a state is in the long run, like Yelp for states.
And Q value?
That's like rating both the place, state, and what you ordered, action.
Value function versus Q value?
Value function is VS, Q value is QSA. One's about being there, the other's about doing something there.
10. What's an MDP?
Markov decision process. A neat package with states, actions, transition probabilities, rewards, and a discount factor.
What's the Markov property?
The future only depends on the pres, just like in my love life. No baggage allowed.
What's the discount factor, Gamma?
It decides how much I care about future closer to 1. I'm patient. Closer to 0. Gimme rewards now.
What's the ultimate goal in reinforcement learning?
To find the best policy that gets max rewards over time. Ideally without rage quitting.
Bellman equation?
A recursive way to calculate value functions. Bellman was basically the Gandalf of reinforcement learning.
Bellman optimality equation?
Same idea but for the optimal policy. Maximum value, baby. Do I try new things or stick to what I know works? Classic dinner dilemma. Epsilon greedy strategy. Pick random actions with probability epsilon.
Play it safe the rest of the time. What are episodes?
A sequence of interactions that eventually ends. Like binge watching. Terminal state. The end of an episode. No more actions.
Time for reflection or snacks. Cumulative reward?
The grand total of all the goodies or punishments collected in an episode. Deterministic equals always do A in state S.
Stochastic equals maybe A, maybe B. Depends on probability. Transition probability?
The chance that action A in state S will land me in state S prime. Like 70% chance I find food.
30% I get lost. Value iteration?
Keep updating value estimates using the Bellman equation till everything converges. Or I lose my mind. Policy iteration?
Alternate between evaluating and improving policies until I strike gold. Policy evaluation?
Estimating the value of a given policy. Sort of like auditing your own performance. Temporal difference. Learn from estimates, not just from full episodes.
TD versus Monte Carlo? TD learns every step.
Monte Carlo waits till the end.
Like instant versus slow brew coffee. What's TD0?
The simplest TD method. Updates from one step look ahead. Next is bootstrapping. Updating using other learned estimates. Sounds like self-improvement books. SARSA on policy TD method. State, action, reward, state, next action. It's a mouthful.
All right, let's dive into some more questions. Q learning.
Off policy. Learns the optimal action value function no matter what actions I actually take.
SARSA versus Q learning.
SARSA plays nice with the current policy. Q learning aims for the best move always.
Off policy algorithm.
Learns about the best policy while following another. Like stalking a mentor while doing your own thing.
on policy algorithm?
Learns the policy it's actually using. Walk the talk.
Eligibility traces.
A way to assign credit across multiple time steps. Basically memory with a decay rate. A blend of TD and Monte Carlo, using eligibility traces.
Choose your flavor with Lambda, model-based versus model-free.
Model-based means learn the world.
Model-free means wing it and learn from experience. Function approximator.
A tool, like neural nets, to generalize across states and actions when you can't store everything.
Neural networks in reinforcement learning.
They help estimate value functions or policies in complex environments. Deep reinforcement learning magic. Alex, next is on cursive dimensionality. As dimensions rise, complexity explodes. RIP simple tables. Adjusting the reward to guide the agent's behavior faster. Like giving treats during puppy training. Next is credit assignment problem, right? Figuring out which past action actually earned the reward. It's like detective work. Real-world exploration exploitation trade-off. Balance trying new things and playing safe.
Like choosing a restaurant on vacation, dead ends in environments.
States where recovery is impossible.
Bad place to be. Literally partial observability.
When you can't see the full picture, like driving in fog.
Partially observable MDP.
The agent works with guesses, not full state info. Next is experience replay. Store and reuse past experiences. Makes training more stable and efficient. Next is sample efficiency. How well the algorithm learns from limited data.
Like acing a test with one night's prep. State abstraction.
Grouping similar states to simplify the problem. Brain hack for agents. Next is reward sparsity. When rewards are rare, making learning slow and painful, like compliments from your boss. My brain is trained. My reward centers are firing, and I'm ready for part 2. Don't miss it. Up next, Deep RL, Actor Critic, and Ethical AI. Stay tuned, folks.